Hello guys, a short video today on a very important and useful device, what is known as a optocoupler or a photocoupler. And what it basically does is provide isolation between the input circuit and the output circuit. And it does that by means of this simple mechanism here. What it has is two components. You have LED here, as you can see clearly, and this is infrared LED. And on the other side, you have here a BJT, a transistor, and this is basically a photo transistor, as you can see with the arrows. So this infrared LED is always shown with two arrows outside because it emits light, and this photo transistor is going to receive that and accordingly control the two collector and emitter, basically gonna connect them just how a normal BJT works, except for normally in normal transistors you apply a base current and the current gets amplified between the much larger current flows from the collector to the emitter. But here there is no separate base. The base is actually controlled by this photo infrared LED, sorry. So yeah, that's what basically optocouplers are. So you give a input pulse or any constant voltage, and accordingly the infrared LED is going to emit light, and your output, basically these 2 points, are going to get shorted because the collector to emitter junction current is going to flow. So this provides what is called as galvanic isolation, because as you can see clearly there is no direct common ground between the two circuits. So you could have something go wrong on this side. Let's say you have a you have a DC-DC converter, say, and there's a reverse voltage spike, or something goes wrong here, a very large amount of current flows. Normally if you would have your two grounds connected in by a wire or something, directly your input side circuit is connected, it would cause damage and all sorts of things would happen. But now it would not happen because only your output side will get affected, and your input side is isolated. So that's what photocouplers are. And the one which I'm going to be, this setup basically of an infrared LED and a photo transistor is suitable for lower to medium frequencies, because all of these are not ideal devices, they have rise and fall times. So this is suitable for say a couple of 10 kilohertz, it seems fine. But above that, you give a faster signal, say 50 or 100 kilohertz, this is not going to be able to keep up with that, and you're going to have a delay. So that's the kind of device we're going to be looking at today. This is the TLP152, it's Toshiba's. That's what I have today with me. This is a high speed optocoupler, and you can push easily greater than 200 kilohertz on this. It's a high speed, and this is slightly different. What it does is it still uses a LED, as you can see written in the data sheet here. It uses a gallium aluminum arsenide LED basically, and on the input side, and the output, unlike the other one where there was a photo transistor, this is actually going to have a photodiode, so which is the opposite of a LED. LED emits light, photodiode receives it and generates a current. So that's what this has. This basically has the LED on the input side and a photodiode on the other side, coupled with the amplifier, because the photodiode is gonna be in millivolts range and the current is gonna be very low, so you need an amplifier. So this, basically this setup is what they called as the photo detector IC, that involves these two components and amplifier and possibly a buffer, something like that. So this is going to be, you're going to be able to push much higher speeds with this. The rise and fall times are very low in this. You can think maybe it's written here somewhere. Yeah, the propagation delay time is 199 nanoseconds, and the other one is 170, which is really low as compared to say a 4N28. That's a popular this kind of photocoupler, the transistor and infrared. Those have rise and fall times in the range of microseconds. So you can clearly see that is microseconds, and this is a couple of 100 nanoseconds. So clearly this is much faster. So today's circuit is just to demonstrate how you can isolate two sides of your circuit. So this is basically an SOIC package, the small outline integrated circuit. It's not the standard DIP we work with, so that is slightly different. The pitch is smaller, But yeah, this is the schematic. This is the same. This is that gallium aluminum arsenide LED. This is going to be your photodiode. This is probably the amplifier. This is the simplified schematic. And the output, that is another interesting thing about this IC. It has a totem pole output, as they say. And what that basically means is, you can see clearly here, this is a push pull output. And that basically means that you're going to be able to source current from your VCC to your output, as well as sink current to the ground. So this is a totem pole output, and since it involves MOSFETs here, naturally the frequency is high, and it can even handle higher currents. And I think this is rated for yeah, plus minus, so sink and source 2.5 amps, which is quite high. So it's a very capable IC. So this is going to be your input, this is your output. So the circuit as such is very, not really very simple, but just for showing you, we have the input here. I'm going to be giving a square wave, and not too high, just 1 kilohertz, but you can push much higher, but just for testing. And we're going to view that on an oscilloscope. This is your input side, and the output side, basically we're going to see the same thing, but as you can see, the source of this is different, and the source of this is going to be different. So here I'm just going to be using a 9-volt battery as your output source, and we're going to be looking at the output waveform also on the second channel of the scope. And normally we use this ground for digital circuits. There's a digital ground, and we call this the analog ground. And here, as such, there's no digital and analog. Just to show you that the two grounds are separate, I use two separate symbols, so you clearly know that the input side has no direct electrical connection. It's optically isolated from the output. So now let's go to the test bench. So yeah, we have the test bench here, and as I said, the circuit is not very complex or anything, and just to demonstrate how it works. So we have the two channels on the oscilloscope here. They are turned on, and what the input, this is basically the input side, and as I said, this is the IC. It's quite tiny, as you can see. And this is basically, the IC is just that small 6-pin IC you see on there. And obviously you can't mount a SOIC is a surface mount package, and dip is through hole. So breadboards are made for through hole. So that's why I got one of these SOIC to dip adapters, as they call it. These are very helpful. Right now I could prototype it because of this adapter. So otherwise you'd have to make a small PCB or something, and again soldering that. But this works nice. This is a nice adapter. So it basically converts the same thing. There are these pads on here, and it's gonna convert to these bug sticks. You can take the output, which is standard 2.54 mm, the through hole dip. That's your standard package. So yeah, this is the input side here. So that's done about the IC. Input side, I'm basically just giving from this basically a 555 timer based stable multi vibrator. And yeah, this is just a small PCB I've made in the past. It gives 50 hertz I think, and 1 kilohertz, and 25 hertz or something, I'm not very sure. But yeah, you can select the frequency, and yeah, just for testing I'm giving a 1 kilohertz. We're going to be giving that to the input side. And the of course you need, as soon as the diode is involved, you need a current limiting resistor. You can just calculate using the same way how you calculate from a normal LED. Whatever source voltage you give minus the drop of the gallium aluminum arsenide diode inside here, that is about 1.4, and the safe amount of current, which is said to be in the datasheet around 20 milliampere. So I've taken around 16, and there's a 220 ohm resistor, so that should be good enough. And this module I'm powering using another 7805 small perf board. I've soldered this 7805, and I'm giving this from a 9 volt, so this 9 volt to 5 volt. And from on the output side here, the data sheet says place a standard 100 nanofarad 104 ceramic capacitor on the rails of the output, for high frequency noise. And so yeah, I've put that. And the output is basically another 9 volt, but clearly you can see it's not the same 9 volt. This 9 volt is separate, this 9 volt is separate. So this is this output side battery, as I said in the schematic. And yeah, we're just looking at the output here on the second channel. Second channel is blue and first channel is green. So now let me just plug in this source here, and you'll be able to see. Yeah, so yeah, the LED is turned on, and you can see on the oscilloscope here, our yellow is our input waveform, that is about 3.6 volts coming in from the module from here. and frequency is around 1 kilohertz, duty is 84%, and the output which we are viewing on the other side, you can see here the voltage is 9.8, which is the battery voltage, and the frequency and duty is going to be the same. And you can see clearly that the two waveforms are exactly the same. And right now it's on 200 microsecond, so even there's a level shift. You can clearly see our input was 3.6 volt, output is 9 volt, and there is no common ground. There's pure optical galvanic isolation here. So I can even zoom in here and go to, you say, yeah, this is in the 100 nanosecond range, which is already quite low. So I can even put a time cursor here, and this basically starts rising at this point, and this starts rising at this point roughly. So you can see this is just around 122 nanoseconds, which I think roughly matches with what the data sheet says on the delay. This is, you can see, that is the delay between the two signals, but that is very abysmally small compared to what our switching frequency is. So if you go into this normal, what we are looking before, clearly, I mean, it's practically the same. So yeah, that was the demonstration. You can, right now, as I said, I'm pushing only 1 kilohertz. You can push much higher and see maybe how the delay is getting changed and all. But yeah, the point was just to demonstrate how optocouplers work. And this side you could not, this is a 555 module, but you could give a optocoupler, you could give a microcontroller, maybe a GPIO output pin, some PWM, say something like that on the input side, and output you connect to, say, a power electronic circuit. You'll get isolation between the two. Your microcontroller remains safe, and the output side power circuit remains separate. So yeah, I hope this demonstration was nice, and learned a couple of things or two about optocouplers. So yeah, thank you.